Here is a differential equation with some initial values given. And this is somewhat special because for this initial value, the power series solution will actually terminate, giving you a polynomial as a solution. Okay, so let me first explain what I mean by a power series solution. A power series looks like a0 x to the 0th power, a1 x to the first power, and so on and so on. The powers change, but they all look like x to some power with some coefficients. Notice that x to the 0th power means just 1, so you can really write this as just a0. And what you want to do is you just want to plug this into the left side for y prime, y double prime, and set equal to 0. And from there you can actually find the solution. So let's try to do it. And it's a good idea to first differentiate before you plug them in. So I'm going to differentiate. And the derivatives are quite straightforward. So x to the nth power, the n comes down, and it will become n minus 1. That's the power rule for differentiation. Differentiate one more time, n minus 1 comes down, so it's n minus 1 an x to the n minus 2. Now, you should also notice that n starts from 1 here and n starts from 2 here. The reason for that is because if you differentiate this, a0, the very first term, will go away, and the series will start from this index being 1. And then differentiate yet again, this will go away at the second derivative, and you're going to start from a2. That's why the n's start from here, 2 here, and then n starts from 1 here. Okay, so now you plug them directly into the differential equation, the left side, and this is what you get. As you can see, all I did was just replace y double prime by this thing, and y prime by this thing in the middle, and y by this thing. And then you try to simplify. The first thing that you can do is to move the 3x inside, 12 inside. And when you move them, x times x to the n minus 1, because x is x to the first power, and the exponents add up, 1 plus n minus 1 just becomes x to the nth power. So if you move the 3x inside, you can combine the x with x to the n minus 1 just to give you x to the nth power. And yeah, I just moved the 12 inside. So that's what you get if you simplify. And here comes the hardest part of this solution. There is the idea of shifting. And basically what you want to do is you want to apply some complex analysis math theorem called the Identity Theorem to solve. And to use the Identity Theorem, you need all the powers of n to match, the powers of x to the match. So I have x to the n, x to the n, that's perfect. But this one, it has x to the n minus 2. It doesn't match with these other ones. So what you need to do is you want to replace n by something else so that this becomes n. And you can easily see that if you replace n by n plus 2, then n plus 2 minus 2 will just be n, right? And that procedure is called shifting. And that's probably the most technical thing that you have to learn. So here's what we do. First, figure out what n should be replaced by. You replace n by n plus 2. And then once you have that determined, you want to replace every instances of n you see in here replaced by n plus 2. So that's what I did. So see, this n is now n plus 2, this n is n plus 2, this n is n plus 2. Don't forget this parenthesis when you do that, okay? When you replace n by n plus 2, this thing still should be multiplied to the rest of them. And if you forget the parenthesis, this n will no longer be multiplied to this. It will just be twice of this one. So that's bad, okay? And then once you have it in this form, then you can simplify them. Notice that you have n plus 2 equals to 2. That you can subtract 2 from both sides, and you just get n equals to 0, right? So you can rewrite that as n equals to 0, and the other ones, well, for example, n plus 2 minus 1 is just n plus 1, so that's why I have n plus 1. And now you have everything as x to the powers of n. Okay, so once you have it in this form, now you can just read off the coefficients. Let's clean out everything else and just focus on this one. These sigmas, they are like factories that that make toys, but not toys. Here they make terms, right? Mathematical terms. And these three factories are making terms, whereas they're starting at different times. So say 0th hour is like the noon. So at noon, the first factory and the third factory is making something, whereas this second factory, they only start working at 1 p.m. The workers come at 1 p.m. and they start producing something. And if you look at what the terms produced are, when you have n equals to 0, you see that the very first one generates 0 plus 2 times 0 plus 1 times a of 0 plus 2, x to the 0th power. X to the 0th power is 1, so you end up with 2 times 1 times a2. So that's what you get. This one is silent. Nothing is coming out from here. They only start working at n equals to 1. This one, if you plug in n equals to 0, you get 12a0. X to the 0 is 1, so we don't care. So you just get 12a0, but don't forget this minus sign. So that's what you get for n equals to 0. On the other hand, starting from 1 and afterwards, all of these produce these terms, right? So if you write them down, these are the things that are produced from all of these factories. And the identity theorem says that all of these individually have to 0. Once you match the powers of x to the n, there's a mathematical theorem called identity theorem in math, which is beyond the scope of this class. But if you accept it, you know that the coefficients should add up to 0. Okay. So this being 0, you can factor the x to the nth power. X in a power series can be any small number, so but it doesn't have to be 0. So this forces this thing inside to be 0. So when you take this inside and set it equal to 0, you have such an equation. And whenever you have such an equation with n's and a n plus 2 a n, you want to solve this for the a with the highest index. N plus 2 is bigger than n, right? These are both n, so we want to solve this equation for a n plus 2. So before I do that, let's factor the 3an out from these two terms so that you get 3 times n minus 4an. Move this term to the right side. Let's see what we get. We get n plus 2 times n plus 1 an plus 2 equals to negative 3 n minus 4 an. And now you just have to divide by this n plus 2, n plus 1 to give you this relationship between an plus 2 and an. What this is saying is that if you know an, then you know the coefficients 2 step afterwards. And because of that, this is called a recurrence relation, because knowing something in the beginning, you know the next one. So this recurrence relation holds. And whenever you have a recurrence relation, you should also write down the starting point of this, because it's not always true. This is only true if all of the factories are working together, and that's true when n is 1 or greater. So when you write down the recurrence relation, write this, and also write down the fact that n should be 1 or greater. So this is what you write. Okay, now you can actually start out by solving individually. The first one is 2a2 is equal to 12a0, and dividing by 2, you get a2 equals to 6 times a0. And then starting from 1, you can actually plug it into this equation to get the value. So for example, when you plug in 1, a3 is negative 3, and then 1 minus 4 is negative 3, 1 plus 2 is 3, 1 plus 1 is 2. So that's what you get. But then you might wonder, well, what is this value and what is this value, right? Then that's when we have to use the initial conditions. See, we had agreed that originally y is written in this form. So if you plug in y, if you plug in 0 into x, then y of 0 would make all of these terms disappear except the a0, right? So you have y of 0 equals to 6 to force a0 to be equal to 6. So that's how you get a0 equal to 6. And then when you differentiate this, then a0 will be gone, but a1 will be now the new constant term. and setting that equal to 0 will force a1 to be 0. So we have the values for a0 equals to 6, a1 equals to 0. Those are perfect. You can plug them back in here, and you'll get the values of a2 as 36 and a3 as 0 from this. Alright, so now let's carry on. Now let's plug in 2. If you plug in 2, you have 2 minus 4, 2 plus 2, 2 plus 1, a4, so this is what you get. And then, again, because a2 is 36, you can definitely compute this. You get the 18. And let's clear some things so we have more room to plug in. Now, the next number is n equals to 3, so you plug in 3 here. Then you get a5 as negative 3 times 3 minus 4, a3. 3 plus 2, 3 plus 1 equal to 0. And then a6 would be a6. Oh, this time, see here it was equal to 0 because a3 is equal to 0, right? But this time a4 is not 0. However, 4 minus 4 is 0. This is 0, so 0 times anything is 0, so you get 0. But one thing that you should notice is that already if a5 is 0, then a7 will be 0 because a5 times something will give you a7. And if a7 is 0, then 7 plus 2, then a9 will be 0. So this recurrence relation says that if something's 0, then every 2 steps afterwards, it's going to be 0. And because you have a6 as 0, when you have a6 0, that would force a8 to be 0. And a10 will be 0, a12 will be 0. So this recurrence relation, if you think about it, it will force everything after 5 and 6 to be 0 because the two steps afterwards will be 0. Okay, so that pretty much settles it. We now know all the values of a0, a1, a2, a3, a4, a5, and so on and so on. So we take the original solution and then plug in the values of 6, 36, 18, and zeros for the other ones. And if you write down what's the survivor, you see that it's 6 plus 36x squared plus 18x to the fourth. So that is the solution to this initial value, this initial value problem. Okay.